Welcome to this Meow seminar, Combinatorial Solving with Provably Correct Results. So we have a trio of speakers today, and before starting the seminar, we'll just quickly introduce ourselves.
Hi, I'm Bart Bogaerts from the Vrije Universiteit Brussel. I'm interested in how logic is used in computer science to solve various types of problems.
I'm Ciaran McCreesh from the University of Glasgow. I'm interested in constraint programming and finding little graphs inside big graphs.
And I'm Jakob Nordström at the University of Copenhagen and Lund University. I've been working on computational complexity, in particular, computational complexity of combinatorial problems. And that's the topic that brings us here today. The revolution that we've seen since the turn of the millennium in combinatorial solvers for problems such as Boolean satisfiability, SAT, constraint programming, mixed integer linear programming. Despite our best efforts at as complexity theorists as proving that these problems are in fact exponentially hard, practitioners insist on solving them, in fact, very, very efficiently, even large-scale real-world problems. There's only one small caveat. Even the very best, most mature commercial tools are sometimes wrong. And just to give some concrete data on this from the 2021 Constraint Programming Mini-Sync Challenge, not because CP solvers would be particularly buggy, but because we have data from that competition. For roughly 1% of instances, we had problems with solvers falsely claiming that instances were unsatisfiable or giving solutions that they claimed were optimal that in fact were not optimal or maybe weren't solutions at all. And it's worth noting that this is not just about a single solver or a problem or some kind of tricky constraint. And it's even in some cases, you can take the same solver, run it on the same problem with the same hardware, and you get different results for different runs. So this problem is worth taking seriously. The reason this is labeled as a controversial slide is, well, maybe you are already taking it seriously and you've really spent time on making sure that your solver doesn't suffer from this problem. Well, in that case, I think you can view the message of this tutorial as giving you the tools to convince others that your solver is different, that your solver doesn't suffer from bugs. So how do we get rid of bugs in solvers or in software in general? Well, the obvious first answer is testing, but clearly that is not enough. I mean, solvers are already tested today, still we have these bugs. And for a more fundamental reason, testing falls short because you can only detect bugs. You can never prove that all bugs have been removed. So a more principled approach is to use formal verification to write down a formal specification of what your solver is supposed to behave like, and then prove mathematically that your implementation adheres to this specification. Now, the problem with this is that current techniques in formal verification are nowhere near to being able to handle the complexity of a modern combinatorial solver. And we see this in the SAT competition, although there's been amazing work on formally verified solvers. They're far behind in terms of performance. And for constraint programming, even dealing with the all different propagator is really challenging. So what we're proposing is to look at what the SAT community has now been doing for a while. They're using proof logging, or they're requiring that their solvers should be certifying, meaning that they output proofs of correctness. And by now there are a variety of different proof logging formats where DRAT is arguably the established standard. And now how a proof logging SAT solver works, or any solver with proof logging, is that you run it on your input, just as before, but you get not only a result, but also a proof file. And then you can take your input, your result, and your proof file, and you can feed it to a standalone proof checker, a dedicated piece of software that checks whether you can trust that the result has been correctly computed or not. Now, in order for this to work, the proof format should be very powerful, very concise, so that solvers can generate these proofs with very little overhead. But on the other hand, the proof format should also be very simple. Writing down proofs should not require intimate knowledge of the finer details of the solver, or because we want verification to be possible by a standalone proof checker that knows nothing about what the solver is up to. So there's a tension here, but it's really, we want to stress again that it's very important that the proof format should be really simple, because that allows your proof checker to be dead simple, so simple that you can convince yourself that it has been coded up correctly. Or if that is not good enough for you, then in fact, since the proof checker is so simple, it should be well within reach of what formal verification techniques can handle, so that you can produce a formally verified proof checker with formal verification tools. So, but the difference from how we talked about formal verification before is that now we don't prove that the solver is correct, we prove that the solution has been computed correctly. And what we also want to argue is that this gives you more than just a guarantee that your results have been computed correctly. Because if you have proof logging in a solver, then you can detect errors even if they are not due to your solver, which is in fact correct, but they arise due to some bug in the compilation phase, or maybe there was a hardware failure. And note that this is something that a formally verified solver would struggle to give you, because even if a formally verified solver is totally correct, you run it on a platform where there is a hardware failure, then you can still get an incorrect result. But if you have proof logging, then this would also screw up the proof, and the proof checker would detect this and complain. Also, proof logging can provide really powerful development support while you're coding up your solver, because even if your solver is passing all the test cases, once you switch on proof logging, the proof checker can detect that maybe your solver is computing these correct results by taking shortcuts in the reasoning. Since the proof that is generated during the solver execution tends to describe what kind of reasoning is being done, this also provides us with a new tool for performance analysis, and potentially also for identifying ways in which solver performance can be further improved. Almost by definition, proof logging enables auditability, because once you've run a certifying solver, you can save the proof log and the computed solution and the input, and then you can run any third party at any later time, can run the proof checker again without even having access to the original solver used to verify the result. And finally, since if you have a proof of optimality, for instance, in your proof log, it tends to prove not only that the solution is optimal, but it tends to explain why the solution is optimal and why a better solution could not be reached. And in that sense, proof logging can help address questions of explainability, which, as we know, is a very big topic in artificial intelligence these days. Okay, so this concludes our attempt at a forceful sales pitch for proof logging. Now, what we intend to do in this tutorial is to tell you about a concrete proof logging system that we have been working on, VeriPB, which is very flexible in that it can be used to support proof logging for instance, subgraph algorithms, for constraint programming, for sophisticated reasoning, such as symmetry breaking, dominance breaking, and all of this in a single unified proof system. So this is what we want to tell you about, but we will start by telling you where all of these ideas come from, because we're relying heavily on ideas from Boolean satisfiability proof logging that we then lift to a pseudo-Boolean setting, which uses the cutting planes proof systems. And for all of these scary words, I'll try to explain shortly what they mean. And again, if you have any questions at any point, feel free to ask, or you can also put questions in the chat. We see we already have a discussion there going on that I will not try to address right now. I think I'll continue with the presentation, and then we can revisit these questions later, I think, when it maybe makes more sense to discuss them. And also they're getting good answers in the chat already. Okay, so I said we would start with SAT. So just to make sure we're on the same page, we're given a formula in conjunctive normal form. That is a conjunction of clauses. Every clause is a disjunction of literals, that is variables or negated variables. Bar denotes negation. So for instance, the first clause here says that P should be true or U should be false. The second clause says that Q or R should be true, etc. And now the SAT problem is there a way to set the variables to true or false in such a way that all the clauses, that all the constraints are satisfiable? Okay, so suppose you run a SAT solver on this problem, and it comes back and says, yes, satisfiable or no, unsatisfiable. What would be a proof of correctness that would convince us of this? That is the question we're addressing. That is sort of the proof logging question for SAT. Well, if you think about it, for a satisfiable instance, it's really straightforward. We can just ask the solver to spit out the satisfying assignment, and it's easy to just plug it in and check that all the clauses, that all the constraints are satisfied. But for unsatisfiability, it's not so clear what a proof of unsatisfiability would be. For us, it will be a sequence of clauses where every clause follows obviously from everything that has been derived so far, including the input formula. And we'll make sure to explain what obviously means in just a little bit. However, the final clause is the empty clause without any literals, meaning it can't be satisfied. That is, it is contradiction. And so we usually write this clause bottom. And since we were able to derive bottom in a logically sound way, this means that the original formula must be inconsistent. And so we've proved unsatisfiability. Okay, so what does it mean to be obvious? Well, one key notion throughout this talk is going to be unit propagation. So for clauses, we say that a clause C unit propagates a literal L to true under a partial assignment row if row falsifies all literals in C except L. So that if I'm not to violate the clause C, which is not allowed, then I just have to satisfy L. So a quick example, here is our example formula again, and I set P and Q both to false. Then the first clause P or not U, in order not to violate it, I have to set U to false. So this clause propagates U to false. The second clause Q or R propagates R to true. And again, I didn't say so, but throughout the talk, 0 will be false, 1 will be true as is standard. And now once I have this assignment, then we can look at the third clause, not R or W, and that propagates W to true. And then it's easy to verify that there are no further propagations. And when we're communicating with the proof checker, one thing that we expect it to understand is unit propagation. So if something follows somehow by unit propagation, we don't need to explain it. We can trust that the proof checker will be able to figure this out. Okay, so as a warm-up now, let's look at a DPLL SAT solver and how we would do proof logging for it. So in DPLL, we assign variables, and then we do unit propagation until either we find a satisfying assignment or we violate the clause, in which case we have to backtrack. And to provide a trace of the solver execution, we can write down when backtracking a clause containing the negations of the decisions or the guesses we made so far, because they were clearly wrong and we need to try something else. So here is our example formula again, and suppose the DPLL solver likes X, so it decides to branch on X and sets it to false. Nothing happens. So it then also branches on Y, sets it to false, and now the clause U or X or Y unit propagates U, which means that the first clause P or not U must unit propagate P to true, but that violates the last clause, and so we can backtrack. Guessing X and Y both false doesn't work, so we have the backtracking clause X or Y. Since Y was the last guess, we backtrack and flip it, and set Y to true instead. And now we see that the clause X or not Y or Z propagates Z to true, but that violates not Y or not Z. So again, this guess doesn't work and we backtrack, but we've tried both values for Y now. So in fact, guessing X false clearly doesn't work. And so we try X being true instead, but now not X or Z propagates Z to true, which violates not X or not Z. So setting X to true also didn't work. So we can backtrack. And now we tried both values of X. And we can conclude clearly that this formula is unsatisfiable. And now the question is, this is an execution trace. How can we turn it into an efficiently verifiable proof? Well, we want the backtracking clauses to be efficiently verifiable. And here we're going to use unit propagation. Namely, we say that C is a reverse unit propagation clause or a RUP clause with respect to a formula or a set of clauses F, if the following holds, that if we assign all the literals in C to false and then unit propagate on the clauses in F, we reach contradiction. Now, if you think about it, if this holds, then clearly F being true forces C to being true, so F implies C, but the point is that we also get an efficiently verifiable condition for this. And now it's a fact that I won't go into, that if you run a DPLL solver and you just write down the backtrack clauses one by one, then they will be RUP clauses. So in fact, this list of clauses that we have is an efficiently verifiable proof of unsatisfiability. Okay, but we're not interested so much these days in DPLL solver, we're interested in CDCL solvers, conflict-driven closed learning solvers. So let's have a crash course on how these solvers work and how you would do proof logging for them. So we start off just as a DPLL solver. We decide or we guess on variables. Here, the CDCL solver guesses that P is false. And then it tries to propagate. Here, the first clause propagates U to false. And we write down the reason clause for this. U is propagated because of the reason clause P or not U. Then there are no further propagations. So the solver sets Q to false. And as we saw before, this propagates R to true by the clause Q or R. And then the clause not R or W propagates W to true. And again, we propagate until there are no further propagations. And there are no further propagations here. So we have to set some other variable. The solver maybe chooses to set X to false now. And now U or X or Y, since U and X are both false, this clause propagates Y to true, and then X or not Y or Z propagates Z to true, but now we have a conflict. The clause not X or not Z is falsified. And just as a piece of terminology, we collect a decision and all the propagations that follow from it into a decision level. So in this solver execution so far, we have 3 decision levels, and we reach a conflict at decision level 3. Okay, and now we want to learn from this conflict. A DPLL solver would just say, okay, I guess setting X to false wasn't so great, let's flip it. But we want to instead compute a reason for the failure in the form of a new clause that we will add to the formula in the hope that this clause will cut away the search space. So to start off this conflict analysis, we look at the conflict clause, not Y or not Z, which wanted Z to be false, but the reason clause X or not Y or Z wanted Z to be true. So clearly they're in disagreement, and we can take the union of these two clauses and remove both Z and not Z, and we get a new clause X or not Y. And it's not so hard to see, if you think about it, that any satisfying assignment to these two clauses will also have to satisfy X or not Y. So any satisfying assignment to the formula will have to satisfy this clause, but this clause is not to be found in the formula. So this is a new fact that we've learned. And we can continue, we can repeat this, look at this clause that wants Y to be false, but this reason clause U or X or Y wanted Y to be true. And again, we take their union, we remove Y and Y bar, and we get U or X, which is again something that has to be satisfied if the formula is to be satisfied, but it's not to be found in the formula. And now, for reasons that we don't have time to go into, this clause contains only one variable at the last decision level, namely X, whereas U is at decision level 1. So the solver likes this clause. It's a so-called unique implication point clause, and the solver decides to learn it and then backtrack, or rather, as we say for SAT solvers, backjump, because we undo as many decisions as we can while this learn clause will propagate. And formally, we go back to the assertion level, which is the second largest level represented in the clause. Here it's level 1. So we keep all assignments at level 1, P and U being false, and then U propagates X to true. And you might say that, well, wasn't this also what the DPLL solver did? But the answer is no, because now this is not a decision any longer. This is a propagation of a new clause. And furthermore, we have undone the decision to Q and the propagations after that, because they were apparently irrelevant here. Okay, so now the solver just continues as before. It turns out that X, not X or Z, propagates Z to true. Then we have a conflict. The conflict analysis is very simple. We just learn the unit clause, not X. And now we can undo all decisions, all guesses so far, because we know that we have now learned that X has to be unconditionally false. So we propagate this. And now the clause we learned before U or X propagates that, well, if X is false, then U has to be true. But then the first clause says, well, in that case, P has to be true. And now we have a conflict again. And note that now we have a conflict, although we haven't made any guesses. So now the solver can conclude that the formula is unsatisfiable. We could, if we wanted to, run the conflict analysis and deduce from this that U has to be false, but that says that X has to be false. But now clearly we have a contradiction because we learned before that X has to be true, but before we learned that X had to be false, so that's contradiction. Okay, so this was like a crash course on CDCL solving, which was maybe a little bit fast if you haven't seen it before. Now we want to prove for this. How would we prove that the CDCL solver has established that the formula is unsatisfiable? Well, the good news, you can, if you didn't get this execution example, that's fine, because it turns out we just need to write down the clauses that the solver learned, and they are guaranteed to be RUP clauses, reverse unit propagation clauses. Now, again, that obviously requires a proof, which we don't have time to give, but let's just see by example. So if I want to prove that this formula is unsatisfiable, I can just write down these three clauses, U or X, and then not X, and then bottom basically saying I'm done, and then claim that these clauses follow all from the formula. Okay, so to see that U or X follows, let's set U and X both to false. That propagates Y to true, which propagates Z to true, which violates a clause, which shows that assuming that this clause is false is clearly contradiction. So anything that satisfies this formula has to satisfy U or X. So we now add it to the formula. And then next we claim that not X has to be satisfied. Well, let's try to prove it by reverse unit propagation. Set X to true. Well, then not X or Z propagates Z to true, which violates not X or not Z. So this proves that indeed any satisfying assignment to this formula has to satisfy not X. And now the final line says in the proof, now you should be able to just unit propagate and see that you have contradiction. And this is very similar to what we did in the last step in the SAT solver. X has to be false. That forces U to false. That forces P to true. And now we have our contradiction. So the point is, and an important point of proof logging is that we can sort of ignore all the details or a lot of the details of what the SAT solver did and just summarize the essence of the reasoning saying, oh, I learned these clauses, and then the proof checker should be able to verify that this is correct. And just to show what this looks like, concretely, so in SAT, there is a standard Dimax format for CNF formulas. Every variable gets a number. So here P is number 1, U is number 4, a minus means a negated literal, and 0 means end of clause. So this is what the formula would look like. And then if we wanted to give the DPLL RUP proof, then it would just be these clauses. X is apparently variable number 6, Y is variable number 7, again, end of clause. And the CDCL proof would look something like this. So this is what SAT solving proofs look like. This is sort of our starting point. This is our inspiration. And now if you want to go deeper into where all of this comes from, reverse unit propagation proofs are in fact just a shorthand for resolution proofs, which you can read more about in the chapter on proof complexity and SAT solving in the second edition of the satisfiability handbook. But it turns out that reverse unit propagation or resolution aren't quite enough for everything that a SAT solver might do. In particular, it doesn't cover everything done doing pre-processing and in-processing. Here's one step that a SAT solver might want to do. It might want to introduce, for some reason, a new fresh variable a, and say that a should be true precisely when x and y are both true. Now, if you think about it, you can achieve this by just adding these three clauses: a or not x or not y, not a or x, not a or y, and these clauses will enforce that a is true precisely when x and y are both true. And if a is a fresh variable, it's kind of clear that you should be fine to add these clauses, because if you have a satisfying assignment to the rest of the formula, this will just propagate the right value to a. And although we don't have time to go into details, if you have the resolution or you have reverse unit propagation plus this rule for introducing new clauses, that's essentially extended resolution, which in turn is more or less equivalent to the DRAT proof logging system that is used in SAT solving. In practice, one very important aspect of proof logging is to erase constraints that you no longer need. From a theoretical point of view, though, from the point of view of presentation of this tutorial, it's trivial to deal with deletions. And so we just ignore them in this tutorial to have one less thing to worry about. This is not trying to sweep anything under the rug. They're just not a problem at all. So in reality, if you're doing proof logging, deletion will be very important. In this tutorial, we'll just ignore it for simplicity. Okay. Good. So we have SAT proof logging. It looks great. Why aren't we done? Well, because it turns out that for some stronger type of reasoning, for instance, in constraint programming, or even in advanced SAT techniques such as symmetry breaking, it's hard to support this kind of reasoning with DRAT proof logging. And also, clauses are not so nice a format to express what more powerful combinatorial optimization solvers in other paradigms might do. So we want something more expressive. And the surprising fact that we claim as an empirical observation is that if we just take what you've seen so far, essentially unchanged, but instead of disjunctive clauses, we will use 0, 1 integer linear inequalities, then everything just works. Okay, if we want to deal with graph algorithms, we can do proof logging for subgraph solving algorithms, although the proof system doesn't know what a graph is. It just knows about 0, 1 integer linear inequalities. As you will see, we can also do proof logging for constraint programming, although the proof system doesn't know what an integer valued variable is even. And we can also do advanced SAT techniques such as cardinality reasoning, Gaussian elimination, or symmetry breaking. And again, we'll try to tell you at the very end of the presentation a little bit about symmetry breaking and how this works. Okay, so now I need to tell you what is this pseudo-Boolean proof logging that we talked about before. What are 0, 1 integer linear inequalities? Well, we'll use as synonyms 0, 1 integer linear inequalities or pseudo-Boolean constraints. They're just inequalities. We have a integer linear combinations of literals, that is variables or negated variables, where it's important to note that xi and xi bar just cancel out and leave a 1. And this linear combination should be greater than some integer. That's what a pseudo-Boolean constraint is for us today. Sometimes it is convenient to require that all AIs in A are non-negative, and you can always do this by flipping between xi and xi bar if you like. For most of this tutorial, we won't really care, but sometimes it's useful. Also, in some of the examples that will follow, we'll think of partial truth value assignments either as the explicit mappings, or we can just list them as the set of literals set to true. Okay, so for instance, rho is the assignment that sets x to true and y to false and z to true. We'll use this notation. Just to make sure we're on the same page as we're approaching these pseudo-Boolean constraints, note that the clauses that we saw before in the CNF formula, they're just a special case of pseudo-Boolean constraints. You take the literals, You sum them up and you say that at least one of them evaluates to 1. That's exactly what a clause is. Now, if you change the right-hand side to something larger than 1, then you get a general cardinality constraint. But then you can also have completely general pseudo-Boolean constraints, which are any integer-valued combinations of literals. So here I've written it in normalized form as x1 times 2x not x2 times 3x3, plus 4 not x4 plus 5x5 greater or equal 7, for instance. So in our proof logging files, we will no longer have clauses, but we'll have constraints of this form. We will also use reverse unit propagation, although this terminology is perhaps not ideal for pseudo-Boolean constraints. If you're coming from constraint programming, maybe you should think about integer bounds consistency instead. If you're coming from a SAT direction, then you should be aware that pseudo-Boolean constraints behave a little bit differently from clauses. They can propagate at multiple different times during the search, and they can also propagate multiple literals in one go. But how do we know? We still want the proof checker to be able to figure out when something propagates. And here's a slide just to try to convince you that propagation is still easy, even if we're moving from clauses to pseudo-Boolean constraints. All we need is the notion of slack, which, given a constraint and a partial assignment, it measures sort of how far the partial assignment is from violating the constraint. And the way to measure this is we look at all the literals that are not falsified by row. So either they're satisfied or they're unassigned and they could still contribute. And we sum up all the corresponding coefficients. We deduct the target, the so-called degree of falsity, the constant on the left-hand side. And the difference here is sort of the margin of error we have. Importantly, now we're using that things are in normalized form so that all integers here are non-negative. And given the notion of slack, it's very easy to see whether something propagates. So here's our example constraint again. Given the empty assignment, we sum up the coefficients, we get 15 minus 7, that's slack 8, and nothing really propagates. But if we set x5 for some reason to false, then we lose the contribution of 5, so the slack goes down from 8 to 3. And note that 3 is strictly smaller than the coefficient 4 of not x4. And what this means is that we cannot afford to mess up x4 as well, because then what remains here is a maximal contribution of 6, which clearly can't reach 7. So purely mechanically, when the coefficient is larger than the current slack, we see that we should propagate the corresponding literal, which doesn't change the slack. Now, suppose for some other reason, because of some other constraints, maybe x3 gets set to false, x2 gets set to true. Well, then we see that the maximal contribution that remains is 4 from not x4 and potentially a 1 from x1, 5 minus 7, that's minus 2. And we already have a conflict. There's no way this constraint is going to be satisfied. And note that one difference to clauses is that we have a conflicting constraint, although we still have variables that haven't even been assigned yet. Now, the point of this slide, if it went too fast, the important thing is just that there is a very simple way of still doing propagation, just as we did before. So we'll be able to define reverse unit propagation in exactly the same way, and we'll be able to decide when we reach a conflict in exactly the same way. Okay? But we will not be able to just write down that everything follows obviously. We'll sometimes need to do explicit derivations on constraints. So some constraints follow from the input. Then we always know that all literals are non-negative. This is just saying that variables are between 0 and 1. And then sometimes in our proof log, we will need to add two valid inequalities, multiply an inequality by a positive number, or divide it by a positive number. And let's just see how this works by a simple example. So suppose that in our input, we have an inequality, a pseudo-Boolean constraint, w plus 2x plus y greater or equal 2, say, then one thing we could do, we could multiply this constraint by 2. That's something that you can do in the cutting planes proof system. Then suppose another constraint in our input is w plus 2x plus 4y plus 2z greater or equal 5, say, then we can add these two inequalities that we have here, and we get a new valid inequality, 3w plus 6x plus 6y plus 2z greater or equal 9. And then we know that z is non-negative. Maybe we want to multiply that by 2 and add to this constraint. And now we note that we have 2z here and 2z bar, 2 not z, and they will cancel and just leave a 2, which we then shift over to the right-hand side. So now we've seen multiplication and addition. Finally, we can divide. Note that all coefficients on the left-hand side are divisible by 3, so we can divide through and get w plus 2x plus 2y greater equal than 7 over 3, so 2 1/3. But note that since everything is integral, we know that if this holds, then in fact, the inequality has to be, the left-hand side has to be greater or equal to 3. And this division and rounding is a very important part. And now, as I said, we want to be able to write this in our proof log. So suppose that we have names C1 or C2 for these constraints, and we are on a way of referring to axioms. In fact, as we'll see later in the talk, we won't have like names of the constraints. We will actually have line numbers that can refer back to constraints. But given that we have this, we could, for instance, write a derivation like this in postfix notation. And the whole point here is just that this is like a simple way to write down the derivation we want, and it should be easy for a proof checker to just perform these calculations and compute this final constraint. So we expect our proof checker, when given explicit instructions to add and multiply and divide, it will do this and it will be able to compute the result. Okay. We will still want to be able to have extension variables. So now they could be, A could be true if this inequality 3x plus 2y plus z plus w greater or equal 3 holds, for instance. And it turns out that you can just write down 2 pseudoboolean inequalities to capture this. The left-hand side one is perhaps easier to see. This says that if A is true, then 3a not A just vanishes. And indeed, this forces the inequality to be true. So this constraint says, well, if A is true, then the inequality is true. The other direction is a bit trickier, but if, given a few seconds or minutes offline, you'll convince yourself that this constraint actually means that if this inequality holds, then A has to be true. So our proof system will allow us to do things like this for fresh variables A. Okay. And now, so what will our proof logs be? Well, again, if we have a satisfiable instance, we can just as before ask the solver to specify what this satisfying assignment is. But for an unsatisfiable instance, we will now have a sequence not of clauses, but of pseudo-Boolean constraints of 0-1 integer linear inequalities, where each constraint again follows quote unquote obviously, either by reverse unit propagation or by small explicit derivations like the one I showed you, or as introducing an extension variable. And again, the proof ends by something obviously false. In our case, it will not be an empty clause, but it will be the constraint saying that 0 greater equals 1. So this is what proofs will look like. We can also support proof logging for enumeration problems where you want to list all possible solutions. So when a solver finds a solution, it can write down in the proof that here is a solution. And the semantics of this is that the proof checker will then introduce a new constraint saying, oh, I don't want to see this solution again. And the final derivation of unsatisfiability then means that, okay, yes, it is true that except for all the solutions that you explicitly told me about, there are no further solutions. So this will be a proof that all solutions have been fully enumerated. For optimization, if you have a linear objective, again, integer linear combination of literals, which we think of as something to minimize. If you want to maximize, you can just negate the objective. There is again the possibility once a solver finds a solution, say some assignment alpha, it can write it down in the proof that here's my new incumbent, it's alpha, and then you have access to a constraint saying, oh, well, in what follows, I want to see a strictly better solution than what I have so far. And this will support For instance, when the solver decides to not explore branches because it can already tell that there isn't a better solution down there, then this kind of constraint can support this type of reasoning. So what I've described to you now, I've given you a whirlwind tour of the vanilla basic VeriPB system, which also supports like nice variable names so that you can write things in human readable form. As we'll see shortly, you can switch on tracing when you run the proof checker so that it tells you what it is deriving. And in particular, if it doesn't like your proof, it tells you why. This is very helpful as you're building your proof logging code for your solver. For the same reason, you also have so-called trust me assertions. If you're building your proof logging incrementally, you can say, okay, I don't know yet how to deal with this part of the code. So just trust me that these constraints are okay. And then you can deal with other stuff. And then you remove the trust me assertions one by one until you have a fully verifiable proof. Okay. And VeriPB, the main developer is Stefan Gocht. And you can look at his PhD thesis to see the full details of this. Okay, so what we've seen so far is I tried to cover proof logging for Boolean satisfiability, and then I tried to tell you how we can take exactly the same ideas, but express them in terms of Pseudoboolean constraints instead, 0-1 integer linear inequalities, and use the so-called cutting planes proof system of reasoning to build proofs that can be verified by the so-called VeriPB tool. And what we will see now in the next of the tutorial, sort of in the rest of the tutorial, so far it's not clear why we're doing this, but now Ciaran will start telling us about some fairly unexpected and amazing things you can do once you have this proof system. And maybe this is, while Ciaran is setting up, we can also take if there are any questions so far.
No questions? Okay.
I have a question. Sorry.
Yes,
Can you
please.
hear me?
Yes.
Yeah. So, thank you for explaining all this. I was wondering. So this proof system obviously uses like multiplication and derivation, right? So, how do I need to think about the library that is doing all those computations? Like, is that verified, or how do I know that that library doesn't make mistakes? Does the question make sense?
I think it makes total sense. I think you're asking, okay, great, but do I have a fully formally verified proof checker for this format? The answer is no, not yet, but as we'll tell you, we're working on it. It's not hard to do. Like all the techniques in formal verification, they're already there. The formal verification people, they know how to do this. So it's just, we need to do it. But you're absolutely right that this is something to potentially be concerned about, especially if you have very big integers, which you might actually have for some applications.
Okay, thank you.
Okay, I guess I'll continue. I'm going to start by looking at the maximum clique problem. So I give you a graph, and we're trying to find a clique, which is a subset of the vertices where every vertex in the subset is adjacent to everything else in the subset. And we want to find a clique that is as big as possible. So in this case, I can show you a 4 clique in this graph, and I'm claiming that this is optimal. So I am claiming that there is no 5 vertex clique in this graph. There are a lot of dedicated solvers for clique problems. It turns out that this problem has applications, and it's also used inside of the solvers as a pre-processing or a reduction step. So there are probably 3 or 4 papers per year introducing new, better maximum clique solvers. The issue is some of these state-of-the-art solvers have been buggy. In a set of experiments I was running, I was finding an error rate of about 0.1% in state-of-the-art solvers. So for 1 in 1,000 or so problem instances, it would output a solution which was incorrect. And although typically the errors we see are off by 1 errors, not always, but sometimes, it's important to note that an off by 1 result inside your clique solver can give you an arbitrarily large incorrect result if you're using clique as a pre-processing step in a different algorithm, for example. So being off by 1 is not just potentially finding a slightly wrong solution. It can have a huge knock-on effect on whatever you're actually solving next. So I'm going to talk you through roughly what we would do to make a proof-logging maximum clique solver. The first thing we need to do is to express the maximum clique problem as a Pseudoboolean problem. The clique problem has several different standard file formats, none of which Proof Verify supports. So we are going to have to deal with supporting these formats. Then we're going to make the solver log its search tree. Now, the solver I'm going to be talking about is effectively a backtracker. So we're going to do something a bit like a DPLL backtracking proof. We need to start by making the solver output a small header. That's easy. Every time we backtrack, we're going to output something. Every time we find a new solution, we're going to output something. And then we have to do a small footer at the end of the proof, which I'll explain. And then the complicated bit is figuring out what to do with the bound function. Most maximum clique solvers are branch and bound, and the bound is where a lot of the cleverness is. And we're going to be going with a slightly different workflow here. So we have an input, which goes into the solver and gives us a result. And we're going to make the solver output the proof. And what we want to do is feed this into the checker again, so that it tells us whether or not we've got the right answer. The slight complication here is that the checker only understands Pseudoboolean problems. It doesn't understand clique. So for now, what we're going to do is we're going to allow the solver to produce the encoding of the input. This is not verified or checked, so we want to do this in a very simple way. We'll get back to this later about what we could do about this. And again, the checker is going to tell us that, okay, assuming that you have encoded the input correctly, then yes, you have given me a correct optimal solution, or no, I found a problem in your proof. Okay, so how do we represent clique in Pseudoboolean formats? And here we're taking a look at the actual OPB file format. So we start with this header line that says, okay, I have 12 variables. They're going to be called x1 through x12. And we have 41 constraints, and we'll see where that 41 number comes from. The first line, we're dealing with an optimization problem. The Pseudoboolean file format only supports minimization. So we're going to have a variable for every vertex, and then we say that the variable takes a value 1 if the variable is present in the clique. So we want to maximize the sum over these variables, or alternatively want to minimize the sum of -1 times these variables. So the way we read this is minimize -1 times x1 plus -1 times x2 plus -1 times x3 and so on plus -1 times x12. And then for every pair of non-adjacent vertices, we're going to have a constraint. So for example, vertex 1 and vertex 3 are non-adjacent. The tilde sign means negate. So I'm going to say either x3 is false or x1 is false. So because there's no edge between 1 and 3, I can't take them both at the same time. Similarly, there's no edge between vertex 2 and vertex 3. So we're going to say not x3 or not x2, not x4 or not x1, and so on. And if we count the number of non-edges, there are 41 of them. So this is where this 41 comes from. Okay. So that's our encoding, and hopefully this encoding is simple enough that we can't really get it wrong. There are better ways of encoding this problem if you're actually looking to give a clique problem to a Pseudoboolean solver, but those certainly are possible to get wrong. Okay, and then let's actually try to write our first VeriPB proof here. What do? We need to start with a header line. So every VeriPB proof starts with this Pseudoboolean proof version 1.2. And then it has one of these lines that starts with an F. F means formula. It means go ahead and load all of the axioms from the input file. And remember, we had 41 constraints. This is what the 41 here says. It says go and take the original 41 constraints from the input. Now, what's the solver going to do? Maybe it will decide to branch accepting vertex 12 and accepting vertex 7 and then accepting vertex 9. And straight away, it's found a maximal, not necessarily maximum clique, but once it's said, yes, I'm including 12, 7, and 9, you can see that you can't include any other vertices. So we're going to log this. We're going to say, okay, I have found a clique of 3 vertices consisting of setting x7 to true, x9 to true, and x12 to true. And I'm going to say, okay, from this is a solution, and you can check this. You can check that this does not violate any constraints. And from now on, I'm only going to be looking for a clique with more than 3 vertices. So I'm going to be looking for an at least 4 vertex clique. Okay. Now, what's the solver going to do? I'm not going to go over details of exactly how clique solvers work in practice, but in this case, it will say, okay, I have branched on vertices 12 and 7. At this point now, only vertex 6 and vertex 9 remain feasible. I can see here that, okay, there is not going to be a 4 vertex clique or bigger here. So I claim we can backtrack from having branched on vertex 7 and vertex 12. So I'm going to write this out as saying either not x12 or not x7 is true. So we have to set at least one of these variables to false. And if you stare at it a bit, this is effectively saying we are deleting that edge in the graph. We're saying that this edge is not going to be present in any better solution. So I'm going to draw it that way. Okay, so now we've branched on accepting vertex 12 only. And we see, okay, we have vertex 1, 6, and 9 are still feasible. And I'm going to claim that the solver will stare at this and say, okay, obviously there is no 4 clique or larger present here. So I'm going to backtrack from having accepted vertex 12. So I'm going to say that not x12 has to be true. And effectively, we're deleting the vertex here. We're saying that vertex 12 is not going to appear in any better solution we find in the future. So I'm going to draw it that way. Okay, now our solver's back at the start. Maybe it's going to branch some more. Maybe it's going to branch accepting vertex 11 and then accepting vertex 10. And if you've done that, then only vertices 1, 3, and 9 remain feasible. And again, I claim a solver is going to look at this and say, aha, it is obvious that there is no 4 clique present, so I'm going to backtrack. So I'm going to say either x11 is false or x10 is false. And again, this is kind of like deleting the edge from the graph, so I'm going to draw it that way. Now I've branched accepting vertex 11. And again, to a solver, I'm claiming that it's clear that there is no 4 vertex clique here. So I'm going to effectively delete vertex 11. I'm going to say that x11 is false. Now the solver branches some more. Maybe it branches accepting 8, 5, 1, and 2. And it says, aha, I have found a 4 vertex clique. I am going to log this. I'm going to say, okay, x1, x2, x5, and x8 gives me a solution. You, the verifier, can easily verify that, yes, this is a feasible solution. And from now on, I'm only going to be looking for a clique that has at least 5 vertices. I claim that in this situation, a solver is going to go, okay, we've accepted vertices 8 and 5. We only have 2 vertices left, so we're obviously not going to get a 5 vertex clique. So we can backtrack from having accepted 8 and 5. Then we're going to backtrack from vertex 8 to just aren't enough vertices to give us a 5 clique at all, so this is obvious. And we're left in this situation. And I'm going to claim that at this point, a solver will just look at this and say, yes, obviously there is no 5 clique present in here. We'll see why this is the case. And I'm going to end my proof by saying, okay, 0 is greater than or equal to 1. So obviously we are in a contradictory situation here. And then the final line of the proof is a C line. This says, okay, I am just asserting that I have actually proved contradiction. The -1 here refers to the previous line. And what I'm saying is I am asserting that the previous line is a contradictory constraint to finish the proof. Okay. So we can take this, we can run it through VeriPB, we give it the Pseudoboolean model, and we give it our proof file, and it says verification failed. Failed in proof line 6, failed to show that not x10 or not x11 have to be true by reverse unit propagation. So this was this situation here. So a clique solver here would say, it is obvious that there is no 4 clique present, But our proof checker doesn't agree with us. It thinks, no, you have to convince me that there is no full clique here. We can also ask VeriPB to give us a trace of a proof. This isn't particularly useful in this situation, but quite often asking VeriPB to trace is very handy. And we can see, okay, it's starting off with the F line in the proof. It's reading in all the constraints in the input. It's giving them constraint numbers 1, 2, 3, 4, 5, up to 41 from the input. Our proof starts by logging a solution. This gives us a solution improving constraint, which is giving number 42. It's okay with this reverse unit propagation step. It's going to give us 43, constraint number 44, and so on until it reaches this point, and it tells us, okay, this is where you've failed. Now, what's going on? To understand this, we need to talk about how clique solvers do bounding. And here is one thing that some clique solvers will do. So I'm going to color the vertices in a subgraph, and I'm going to give adjacent vertices different colors. And I'm going to try to use not too many colors, but this is hard, so I'm just going to do a greedy coloring, for example, and I've done that. What I claim is, if I can color a graph using k colors, then you cannot have a clique of greater than k vertices present in that subgraph, because every vertex in a clique definitely has to be given a different color. And in fact, in proof terms, what I'm really saying is that every color class we find is describing an at most one constraint. So in this example, I am saying that, okay, here is a coloring. You can check that adjacent vertices have different colors. For example, 1 and 2 are adjacent, so they are different. 1 and 3 can take the same color because there's no edge between them. I am claiming that the red color class, so color class 139, is really an at most one constraint that I've found. So I'm saying at most one of x1, x3, or x9 can be true. And similarly, at most one of x2, x4, and x7 can be true. And this kind of reasoning, this does not follow by reverse unit propagation. This is us doing something clever here. So we're going to have to justify this somehow. Now, one thing we could say is, okay, let's just list every single color class that we might use as part of the input. The problem here is there are exponentially many color classes. We don't know which ones we're actually going to use in practice. So we can't just pre-generate every single color class we might use and treat it as part of the input. So instead, what we're going to do is use cutting planes to recover color classes lazily. Here's an example. This is looking at the x1, x6, x9 color class. We have a constraint saying, okay, we can't take both x1 and x6. We have a constraint saying that we can't take both x1 and x9. And we have a constraint saying we can't take both x6 and x9. So I'm going to add all three of these together. So I get 2 not x1 plus 2 not x6 plus 2 not x9 is greater than or equal to 3, just by addition. Then I'm going to divide this whole thing by 2. So 2x1 becomes x1, 2x6 becomes x6, 2x9 becomes x9, 3 becomes 1.5, but we're dealing with integers, so we round this up by 2. So here I'm saying that not x1 plus not x6 plus not x9 is greater than or equal to 2. So I've got 3 variables, and I'm telling you that at least 2 of them have to be false. So really I'm saying, okay, at most one of them can be true. So just using a few additions and a division, we can generate the at most one constraint when we need it. And I claim that this generalizes for arbitrarily large color classes by a simple induction argument. And in particular, every non-edge constraint in the color class is used exactly once. And we only have to do a few multiplications and divisions, which are based upon the number of vertices we have. So somehow I claim that this is an efficient proof, that we're using each piece of information exactly once, and we're getting something that's somehow effectively linearly sized in terms of what we're dealing with. The other important thing here is that a solver does not need to understand cutting planes to be able to write this kind of proof. You can do this purely mechanically. You do not need inside your solver a Pseudoboolean constraint object or anything like that. You can do this purely through a very stupid for loop that writes out text with no kind of reasoning going on. So what does this look like in practice? Here is an actual VeriPB proof that I have syntax highlighted slightly. As before, we start with a proof header. We start by logging the first solution that we find, the 3 clique, and doing a reverse unit propagation step. Star lines are just comments. These are handy during debugging. Now I'm going to do an explicit cutting planes derivation. And what I want to say is take the constraint that says 1 is not adjacent to 6, and the constraint that says 1 is not adjacent to 9, and add them together. And then take the constraint that says 6 is not equal to 9, and add them together. And then divide the whole thing by 2. Now, when we're referring to constraints in a VeriPB proof, we do it by constraint number. So this is, for constraints that were in the input, it's just effectively the line number in the input, ignoring the header. So maybe the constraint that says not x1 or not x6 is the 7th line of the input. The constraint that says not x1 or not x9 is the 19th line of the input. And the constraint that says not x6 or not x9 is the 24th line of the input. So anything I've written in a little gray subscript here is just me explaining what these numbers mean. It's not in the proof. So the actual line in the proof would say P7, 19 plus 24 plus 2D. I'm just using the syntax highlighting so that you can tell that 7, 19, and 24 are constraints in the input, and 2 is a numerical constant used for division. Then we have to add constraint 42 to the previous constraint. I'll not go into details of exactly why, but constraint 42 is our objective constraint, and -1 just means the previous line. And this is then enough to let us backtrack and say, okay, now not x12. And again, here we have a color class x1, x3, x9. So I'm looking at the x1, x9, x3 constraints, adding them all together, dividing by 2. Here we have another color class, and then right at the end, in fact, we're dealing with 3 different color classes to backtrack from from not having made a guess. So I have the 1, 3, 7 color class, I have the 2, 9, and 4 color class, and so on. And somehow I'm adding all of these together, and I'm adding them to the objective line. And that gets us our contradiction. And we can run this through the proof checker. And this time we say, okay, VeriPB, give me the trace. You can see it's reading in the input. It's doing something with objectives. Here we have an explicit cutting planes derivation. So I say add constraints 7, 19, and 24 and divide the whole thing by 2. And it is printing out, okay, I did this and I got not x1 or plus not x6 plus not x9 is greater or equal to 2. So I'm telling you that 2 of these 3 things have to be false. So at most one of them is true. And so on until we get to the end and we get verification succeeded. So far, so good. Now, I've told you about one hypothetical clique algorithm, which is not quite as smart as any of the algorithms in the literature. So what do clique solvers actually do in practice? So a big thing is finding out a really good search order for branching on vertices. This is completely irrelevant for proof logging. All the solver has to do is output backtrack constraints as it did them. It never needs to justify, I branched on vertex 6 because, or I branched on vertex 9 because. It just says, well, I did this and I got a contradiction. Clique solvers will tend to use local search to try and find a strong initial candidate. Again, we don't need to justify any of the local search. We just need to say, aha, here is a clique. You can easily check that this is a clique and take it from there. Different bound functions. This is where things get interesting. We don't know if a cutting planes is strong enough to justify every useful bound function that anyone will ever invent. But it seems to be strong enough that we have efficient proofs of everything that people have come up with so far. And then people also want to solve weighted clique problems in practice, and there are clever ways of doing this. It turns out that literally the only thing we need to do is add a multiplication to the proof step, and it all just works. And this is over a very wide range of algorithms that people have come up with. So somehow it seems that cutting planes is strong enough to efficiently justify all the really clever combinatorial algorithms that people have come up with so far. So far, so good. Is now a good time for a break? I think I will pause for 5 minutes, and Jakob is muted.
Indeed, I am. So yes, let's take some questions, and then if after the questions, let's take a 5-minute break, and then we'll continue after that. First, if there are any questions at this point. I mean, we had one discussion going on in the chat is that, okay, what about multi-threaded solvers, that it's hard to make solver deterministic? And one way to respond to this is, yes, this would just make proof logging seem even more important. And you could argue that one problem when doing proof logging in a multi-threaded solver is to know in which order you should add the constraints in the proof log that you're generating. But I would argue that, well, that's no harder than the different threads in the solver figuring out in which order they go. So I don't see any really foundational challenges, new challenges for proof logging in multi-threaded solver, but I see that Ciaran wants to add a comment to this.
Yeah, I think if you're dealing with a work stealing solver where you're allowed to steal from stolen work, then it is actually a proper research challenge to figure out how to turn this back into a proof. But certainly you can do it, but whether you can do it without having to linearize it, so effectively doing a full linear scan, I don't think this is immediately trivial. I think it's doable. I think it's doable using extension variables in a clever way, but I don't think this is trivial.
I think you're pointing out another relevant challenge is also if you're using a massively parallel solver, then ideally you'd like to also be able to verify the proof in parallel, because you were saving a lot of time by solving the instance in parallel. Now, if your proof logging is sequential, then you're losing all of this. Maybe. And that is definitely like parallel proof checking, I guess, would be a challenge. But it's not like it's fundamentally impossible or anything, but yeah, definitely would require research.
May I ask a question about this proof logging for graphs?
Yes.
So if I understand correctly, you keep your subgraph algorithm exactly the same, and you translate everything it does as PB constraints, right?
Yes.
So, and you showed for one thing for this color computation that allows you to decide, but I guess you have many more. So do you have some of the features you cannot translate into Pseudoboolean constraints reasoning?
For clique algorithms and subgraph isomorphism, we have not found any so far.
Oh.
Same for constraint programming. But I suspect we will run across them in constraint programming at some point in some area. But it seems that all the clever combinatorial arguments that people come up with come down to, for example, counting things in very clever ways. And somehow cutting planes is strong enough to express those, or at least strong enough to justify them. Okay, so does it mean that if you have an efficient cutting planes PB solver, you should be able to solve efficiently those problems too? No, because just because we can output cutting planes derivations and things does not mean that a Pseudoboolean solver would actually find them. Yeah. Well, I'll show you an example later on for the all different constraint. That in principle, Pseudoboolean solvers could recognize all different constraints and do all different reasoning, but in practice, probably they won't recognize them. Okay. Yeah. So the issue is, how would you do that specific reasoning with a cutting planes by solver? Because in your case, you guide them, so you know to guide them. Okay. Yeah, and it's a bit like saying, okay, this problem has a short resolution proof, but that does not mean that a solver will actually find that short resolution proof. Yeah. Okay. Thanks.
Okay, if there are no other questions at this point, then let's take a 5-minute break, and we'll be back after the break, continue with some more graph algorithms, and you can see a little bit about constraint programming, and then hopefully more about symmetry breaking and other powerful methods in advanced stat solving. But right now we are taking a break. So we're back from the break, and Ciaran McCreesh will continue by telling us about subgraph algorithms. Please, Ciaran.
Yes, so subgraph isomorphism. We are given a little graph, which we call the pattern, and a big graph, which we call the target, and we want to find the little graph inside the big graph. So, for example, like this. This has a lot of applications in compilers, biochemistry, model checking, pattern recognition, etc. This is another problem that people actually want to solve. And often they want to find all matches, so they want to be sure that they haven't missed anything. Okay, we're going to go through the same process. We're going to discuss how to represent subgraph isomorphism in pseudo-Boolean form. And then we're going to see some examples of proof logging for some of the things that the state-of-the-art solver does. So let's start by looking at our variables. I'm going to use these xpt variables. This xpt is true if pattern vertex p gets mapped to target vertex t. So we're going to have one of these for every pattern vertex for every target vertex. And I'm going to say here that every pattern vertex has to be mapped to exactly one target vertex. So sum of the xpt's for a given t is equal to 1. Okay. And then typically we're looking for an injective mapping. So every target vertex may be used at most once. So summing up over p, I'm going to say that I want to say that the sum over my xpt's is less than or equal to 1. But we have to write this as a greater than or equal to, so I'm just going to multiply the whole thing by -1 and flip the signs. So if you stare at it a bit, you can see that, okay, this constraint is saying that every target vertex can be used at most once. And then we have the tricky constraint, which is dealing with adjacency. So what I'm going to say is either vertex p does not get mapped to vertex t, in which case it's fine, or if it does, then each of p's neighbors must be mapped to one of t's neighbors. So I'm saying either p doesn't get mapped to t, or for any vertex that's adjacent to p, I have to map it to something that's adjacent to t. Again, you can stare at this for a while until you've convinced yourself that this is expressing the edge constraints. Now, it turns out that subgraph isomorphism solvers do a lot of very clever graph-related things. Here is one example. So suppose I have a pattern vertex which has 3 neighbors. I claim it is never possible for this vertex to be mapped to a target vertex that only has 2 neighbors, because each of my neighbors has to be mapped to somewhere else. And in general, if I have a pattern vertex of degree p, I cannot map it to a target vertex of degree p minus 1 or lower. Looking at the example in the top right here, we're going to say that pattern vertex p cannot be mapped to target vertex t because p neighbors q, r, and s would all have to be mapped onto u and v, and there are only 2 places for 3 things to go. So in proof logging terms, we need to justify that not xpt is true. How do we do this? Okay, let's start off with the adjacency constraints. So either p does not get mapped to t, or q has to be mapped to either u or v. Either p does not get mapped to t, or r has to be mapped to one of u or v. And either p does not get mapped to t, or s has to be mapped to one of u or v. Okay, so I'm going to take these 3 constraints, which are part of the input, and I'm just going to add them together. So I get 3 not xpt plus xqu, xqv, xru, xrv, xsu, xsv is greater than or equal to 3. So you can see if I set this, so if I don't map p to t, then I get my 3, so I can ignore the rest of the constraint. But if I do map p to t, then somehow I have to get 3 out of this remaining part of the constraint. Okay, so here's where we are. Now, Remember, we have injectivity constraints for U and V. So I'm saying that U can be used at most once between O, P, Q, R, and S. This is an at most one constraint. And similarly, V can be used at most once between O, P, Q, R, and S. And what I'm going to do is I'm going to take this sum and add these two things. And putting this together, we get 3 not XPT plus, and then all the XQUs, XQVs, XRUS, XRV, XSU, and XSV cancel out. We're left with the XOU, the XPU, the XOV, and the XPV, all in negative form. And then we have the 3, a -1, and a -1. We're left with 1 here. And I claim that at this point we're nearly finished, because if you look at these are 0, 1 variables, so they're going to be 0 or -1. We're trying to get that not XPT is greater than or equal to 1, and these can't contribute anything, so we're effectively there. So what do we do? Remember, we're allowed to assert that any variable, any literal is greater than or equal to 0. So we have these constraints: XOU is greater than or equal to 0, XOV greater than or equal to 0, XPU greater than or equal to 0, XPV greater than or equal to 0. We're just going to add all of these together. These cancel. We end up still with a 1 on that side. So we're saying 3 not XPT is greater than or equal to 1. And then we divide by 3 to get not XPT is greater than or equal to a third, i.e. not XPT is greater than or equal to 1. So again, we've seen that cutting planes can somehow express this counting argument in a very compact and efficient way. Looking at this in VeriPB, and again, the subscripts here are just convenient so that you can tell where numbers are coming from. They're not part of the proof. Suppose that the constraint that says if P gets mapped to T, then Q has to go to one of T's neighbors is number 18. PT and R is 19, and PT and S is 20. So I'm going to say add constraints 18 and 19, then add constraint 20. Then add our injectivity constraint, which might be line number 12 in the input. Add our injectivity constraint, which might be line number 30 in the input. Add the literal axioms, and then divide the whole thing by 3. Or somewhat simpler, and it turns out this is convenient for solver authors, VeriPB can actually do the last bit of simplification automatically. There is this notion of syntactic implication, which can do some very simple implications for you. So what I can just say is, okay, add the 3 adjacency constraints and the 2 injectivity constraints. And then you should check that the previous constraint that I created implies that XPT is false. So that's all we need. Now, subgraph isomorphism solvers do all sorts of clever things. They do reasoning about injectivity and counting. They will look at the distance between vertices. They will look not just at degree, but something called neighborhood degree sequences. They will do filtering based upon the number of paths between vertices. There are these things called supplemental graphs, which give us even more constraints. And it turns out for every single step that is used in the state-of-the-art solver, somehow we have efficient ways of justifying this reasoning using cutting planes. So for example, if I have an order n cubed pre-processing algorithm, then somehow it takes me at most n cubed steps in cutting planes to output a justification of what's going on. Ignoring a small log factor here, we're effectively saying that the length of the proof steps are no worse than the time complexity of reasoning algorithms. And this is genuinely fairly trivial to put inside a solver. It's not like we have to do a huge amount of additional work to be able to output these cutting planes proofs. And again, we can do all of this without writing a solver that understands cutting planes. So all of these proof steps I can output by simple text and string manipulation here. There are limitations of this. So for both clique and subgraph isomorphism, we are relying upon the Pseudoboolean problem being encoded correctly. It turns out, work in progress, we can probably formally verify the correctness of the encoding. So this is within reach of formal verification, but we can take a proof tool and we can say, okay, it is the case that there is a solution to this Pseudoboolean problem, even only if there is a solution to this graph problem expressed in graph theoretical terms. So this should be formally verified. Proof logging is relatively slow in this case. We do get large constant factor slowdowns. The reason is that subgraph algorithms do an awful lot of very clever bit parallel propagation. So when we're taking an operation which is previously just an operation on a bit set, which might take 10 clock cycles, and then say, now you have to write out to disk a statement saying that you did this, we are seeing potentially large constant factor slowdowns. The interesting thing is that it is only a constant factor slowdown, though. Verification can be even slower. The proof verifier has to do unit propagation, which, although we think the unit propagation is fast, it is much, much slower than what bit parallel algorithms can do. For example, in a clique solver, we can do a full set of coloring in maybe 100 clock cycles for a typically sized graph with 1,000 vertices. There is no way that you can get close to this if you have to do unit propagation. But this works in practice up to at least moderately sized hard instances. We do need to be a bit careful. The Pseudoboolean encoding can get quite big, and even cubic encoding like the subgraph isomorphism will sometimes be painful. It's particularly bad when we're talking about large sparse graphs, which are computationally tend to be quite easy, but the encoding gets very big. But it does work at least on moderately sized instances, which is an awful lot better than anything that we've had previously. There is an implementation. You can go and play around with this as much as you want. The Glasgow subgraph solver is state-of-the-art for subgraph isomorphism, and we can proof log every single thing that this solver does. Moving on to constraint programming now. So in constraint programming, we have non-Boolean variables. We have variables that can take their domains from a finite range of values, typically integers. We have lots of different kinds of constraints. So we might have an all different constraint. We might have some arithmetic constraints. We might have a constraint saying that, okay, this sequence of variables must match the following regular expression and so on. So we'll need some way of encoding all of these constraints down to pseudo-Boolean form as well. And we'll need some way of justifying every kind of inference that every constraint propagator ever does. Constraint programming solvers do a lot of clever reasoning that exploit the high-level structure of constraints. So somehow we have to justify this. And we have to do reformulation. So in the constraint programming world, it's quite common to take a problem that is specified one way and to look at it and be very clever and say, okay, I am going to represent this problem in a different way, or I am going to represent these constraints in a different way, and then solve this. And somehow we have to be able to verify we're doing this correctly as well. Let's start with compiling constraint programming variables. I'm going to use capital letters for constraint programming variables and lowercase letters for pseudo-Boolean variables. Here's one thing we can try. If I give you the variable big A between -3 and 9, we can use something that's called direct or one-hot encoding. I'm going to introduce these variables A equals -3, A equals -2, A equals -1, and so on. And I'm going to tell you that exactly one of these variables has to be set to true. The problem here is this doesn't work for large domains. People in constraint programming, particularly if they use high-level modeling languages, might give you a domain that runs between 1 and 1 million. This is going to kill you if you try and use the direct encoding. We could use a binary encoding here. I'm going to say that this is A bit 0, A bit 1, A bit 2, A bit 3. And I'm going to say that 1 times the 0 bit plus 2 times the 1 bit plus 4 times the 2 bit plus 8 times the 3 bit is greater than or equal to -3. And then if you stare at this negative term a bit, this is effectively your 2's complement bit. And similarly, to specify that it has to be less than or equal to 9, I have the negatives here and greater than or equal to -9. So we can use this encoding and it's much more compact. If you've ever tried to solve problems specified this way, you'll know that this is a terrible encoding. It doesn't propagate. You really want to avoid using this if at all possible. Turns out for proof logging, this isn't a problem and we can just use this encoding. And in fact, we can mix this binary encoding in something which is sometimes called an order encoding. So whenever we need it, we're going to define, for example, A is greater than or equal to 4 to be true if and only if the sum over the bits is greater than or equal to 4. Similarly, A is greater than or equal to 5 if and only if the bit representation is greater than or equal to 5. And I'm going to define A equal to 4 if and only if A is greater than or equal to 4 and A is not greater than or equal to 5. And then there's a little bit of bookkeeping. We're going to create some additional implication constraints just to help with propagation. Now we can do this inside the Pseudoboolean model if we are actually talking about variables giving a specific value. But here's where we're using extension variables. We can introduce all of these A equals 4 and greater or equal to 4 variables lazily during proof logging. So if we have a constraint programming variable that has 1 million values, and straight away we knock it down to 10 possible values, those are the only 10 values that somehow need to appear in the proof. So somehow we have this way of supporting both very large encodings and encodings of a very strong propagation property. What about compiling constraints? So we need to compile every constraint down to Pseudoboolean form. This does not need to be a propagating encoding. It only has to be an encoding which is obviously correct. And we are allowed to use additional variables when we're doing this. For example, using uppercase for CP variables, 2 big A plus 3 big B plus 4 big C is greater than or equal to 42, where all my A, B, and C is run from -3 to 9. I'm going to take my sum over my bits for A and multiply it by the 2 coefficient, so 2 times bit 0 and so on. Same for B, multiplying the coefficients by 3, and same for 4, multiplying the coefficients by 4. And I end up with this Pseudoboolean constraint, which means the same thing. So that's easy to compile. What about other kinds of constraints? So another type of constraint is called a table constraint or an extensional constraint. This is just a list of feasible combinations of values for a particular set of variables. So for example, we might have a table constraint that says ABC has to take 1 out of this list. So either A is 1 and B is 2 and C is 3, or A is 1 and B is 3 and C is 4, or A is 2 and B is 2 and C is 5. So I'm going to define this by introducing these T variables. These are just 0 and variables. I'm going to say if you take T0, then A equals 1 and B is 2 and C is 3. If you take T equals 1, then A equals 1 and B equals 4 and C equals 4 and so on. And you have to pick one of these T variables to be true. And it turns out we can write these implications conveniently in Pseudoboolean form like this. So we get the 3 either by setting the selector variable to false or by setting all 3 of the Boolean variables in the correct way. And in general, we know a lot about compiling constraint programming constraints down into lower level formats. So we already know, so for any constraint where somebody knows how to compile it using CNF or integer linear inequalities or table constraints, possibly using auxiliary variables, the compilation is a solved problem, particularly because we don't need a good compilation, we only need a correct compilation. Constraint programming solvers do backtracking search. Mostly this works as we've already seen, there's not much new to say here. Constraint programming solvers do restarts. Again, it turns out this is extremely straightforward. And again, we don't need to justify guesses or decisions. The way we set things up, we only need to justify when we backtrack. So when a constraint programming solver backtracks from having guessed A is 1 and B is 2 and C equals 3, we need to justify this, but we don't need to say why the solver decided to branch on A is 1 and B is 2 and C is 3 or anything like that. Okay, how do we justify the inference that all of these constraints do? Well, if it's something that follows some unit propagation, then nothing is needed. If somehow the Pseudoboolean encoding propagates the same way as a constraint programming solver does, we don't need to do anything. A lot of propagator steps are effectively doing a little bit of look ahead in a very efficient way. In this case, we can just output a reverse unit propagation step in the proof for whatever this look ahead is. But some constraints actually need explicit cutting points derivations. For example, linear inequalities, to justify them, we need to say add these things up and multiply and so on. All different is a bit more complicated, and I will give you an example of this. So we have 5 variables, v, w, x, y, z. V is either 1, 4, or 5, w is 1, 2, or 3, and so on. A constraint programming solver will look at this and say, aha, this is a contradiction. You can't do this. And the reason it will do it is because it will spot that we have 4 variables, w, x, y, and z, that only have a total of 3 different values between them. So we know that w, x, y, and z between them have to take the values 1, 2, and 3, and they all have to take different values. And there just aren't enough different values to go around. So obviously this constraint is contradicting. How do we justify this in cutting points? Well, we know that either w is 1, or w is 2, or w is 3. We will have a constraint somewhere that says this. Similarly, x is 2 or x is 3, y is 1 or y is 3, z is 1 or z is 3. And then going down the columns, we also have a constraint that says that the one value can be used at most once between v, w, y, and z. So again, this is an at most one constraint. Similarly, the w and the x's, so the 2 value can only be used once, the 3 value can only be used once. And if you add up all of these constraints and all of these constraints, then nearly everything cancels out. And we are left with saying negative v equals 1, so this little bit here has to be true. Now, why is this a problem? Well, this is a 0, 1 variable. So negative of it is going to be either 0 or -1. So there's no way it's going to be greater than or equal to 1. So again, we can add the literal axiom. So we can just assert that v1 is greater than or equals 0, add these together, and we get 0 is greater than or equal to 1, which is a contradiction. And it turns out that we can always follow this process for all different reasoning, including where all different is used for propagation rather than for detecting a contradiction, and including where this is done conditionally. So if I have guessed that A is 2 and B is 3, then we can do all of this. And again, it's a purely mechanical process that you can just say, okay, add up the following constraints, and then VeriPB will automatically check and simplify down to get you the right answer. So no cleverness needed there. And additionally, it's worth pointing out if you do know the all different algorithm, but the all different algorithm, when it fails, you can actually easily get it to tell you, okay, which of the k variables that don't have at least k values between them. You can spit that out trivially. Okay, reformulation. I will not go into heavy details of this, but we have a paper showing how to do things like auto-tabulation. We can even re-encode things like maximum common subgraph as a clique problem without changing the inputs. We can handle some very clever reformulations fully inside the proof system. Big challenge here is high-level modeling languages. Languages like Minizinc and Essence have their own complicated compilers. So even if we can solve the problem of making sure that we're compiling constraints correctly, how do we know that we're giving a proof of the problem that the user actually specified? This is future research. And again, we have an implementation available, and there is a paper that explains how all this works. This is certainly not the state of the art in constraint programming solving, but it is a fully featured constraint programming solver with a small number of global constraints so far. Performance-wise, this solver does actually perform pretty close to state of the art if you are only using the following global constraints. And there are details in this paper if you want to see how it works, or you can download and run it. And I believe I will stop there and hand you over to Bart for take any questions whilst Bart sets up screen sharing.
So are there any questions at this point?
Yeah, maybe one question. I think it's interesting that you mentioned that the encoding, the PB encoding can be quite different when you log and when you want to solve. because of the propagation feature, or yes, feature that you have, whether you are consistent or not. So what do you think is really important for a good logging encoding? So is it the simplicity of the steps, or or is it the compactness, or?
Compactness is certainly a desirable property in some situations. I mean, the simple example, just of compiling variables, the binary encoding is probably not the simplest encoding, but the direct encoding is just too big and will kill you. So we need a compact encoding, and then subject to that, we want it to be as simple as possible. And then anything clever we're going to introduce inside the proof rather than inside the problem definition. So one way you can think about this is somehow the constraint programming solver can lazily introduce really good encodings when it needs them.
Yeah.
And the rest of the time, it's just running off a compact encoding, and then subject to that, a simple encoding.
Okay. And one other point I was thinking about is when you do this translation from one solver to the PB logging format, you need to have a 1-1 correspondence if you want to debug. Right? If you are incorrect, or well, if you find an issue in the logging, if you want to find out where it comes from.
Okay, so this is a tricky question. We have sort of hand-waved this in publications so far, and it hasn't been a problem. It's also for enumeration and counting, it's a bit of an issue. My PhD student, Matthew, is currently trying to take everywhere where we have said it is obvious that this works, and is writing a formal proof that yes, our encodings are correct, etc. He is running into exactly this issues of one-to-one correspondence, and do we have these consistent encodings or not? I would say that the answer is that so far we can get away with using an arc-consistent encoding. So we do have this one-to-one property.
Okay.
If this is not desirable, and in some cases it isn't, we can do some very clever tricks using extension variables to get rid of this. But this is sufficiently complicated. This is probably a paper in its own right on how to do this.
Okay.
So ask us in 6 months, and hopefully Matthew will have a very comprehensive answer to this one.
Okay. Yeah, no, because that's always the issue when you do encodings, and when you if there is a problem in your encoding, you want to find out, and then you need to do F-1 to try to understand where it comes from. Okay. Thank you.
I had a small question as well. So you said that as far as you've encountered, all the propagation algorithms can be given proofs in cutting planes. So far. So my immediate guess would be things like there are some scheduling propagation algorithms that do fairly intricate stuff that is not at all obvious, like Willems omega trees and stuff like that. Do you believe that these will be amenable to cutting planes as well, or?
I think if we are allowed to use extension variables and symmetry and dominance reasoning and various other clever tricks, then I'm not going to say we can do these with no overheads, but I am fairly sure they are doable with low polynomial overheads.
Okay. So it's not easy, but it can be done, you think?
I think it is potentially doable.
Okay.
And even in the cases where it might end up being difficult, there is probably a practical solution we can get away with.
Yeah. So and related to this, there's you previously said that okay, when we do a branching decision, we do either A or B. And it's quite common, for example, if you use an edge finding that you actually store a branching decision that task A is before task B or task B is before task A. So you have implicit in this branching decision that A and B do not overlap. So that's a propagation step, but it's never actually spelled out. Would you have to spell it out in the proof, or?
So you would have to introduce an extension variable. So A, if and only if task 1 occurs after task 2, and then you would need to strengthen one of the 2 constraints to say, oh, and actually they can't overlap.
Okay.
And then you would write it out like you're branching on the extension variable.
Okay. Yeah. Quite interesting. Thank you.
All right. If there are no further questions, then I'll deliver the rest of this presentation. So you might have seen this was announced as a plus or minus 2-hour tutorial. And if you look at the slide numbers, it looks like we're on the plus side. Let's get into it. What I'll do now in this last part is first I'll give you the truth about extension variables. So we've talked about them already and we've used them a lot, but I'll show you exactly how you can do that in the VeriPB proof system using the redundance rule. These extension variables themselves, they have some nice applications as well, but I'll probably just skip these. If you're interested in parity reasoning or translations of Pseudoboolean constraints to CNF, you can have a look at the slides afterwards, or just ask me some questions about it. But what I'll say then is, well, this redundance rule, if you go to an optimization problem instead of a decision problem, well, there's 2 possible extensions to it. And one of the extensions is really suitable very well for doing things like symmetry or dominance handling. So, extension variables. Remember, we wanted to have, well, a new fresh variable, in this case A, encoding, for instance, that A is true if and only if X and Y are both true. And we can do this with clauses, or we can do this with Pseudoboolean constraints. And if you want to use things like resolution or cutting planes, you can never ever derive these blue constraints. And why not? Well, because they're simply not implied. They're talking about a new variable that the original formula doesn't even talk about, so you can never derive this with a, well, logically sound proof system. But if you go to richer proof systems, you can derive these, and that's what we're going to do now. To show how we do this, I'll introduce the notion of a redundant constraint, and I will call a constraint C here redundant with respect to some formula if adding the constraint to the formula doesn't change the satisfiability. So clearly, it's not going to make an unsatisfiable formula suddenly satisfiable, but it can also not make a satisfiable formula unsatisfiable. And as long as you're only interested in decision problems, adding redundant constraints should be okay, because you're not turning an unsatisfiable problem into a satisfiable one. And in general, it's hard to know whether a constraint is redundant or not, but here's the characterization of it. And before we look into the details, I want you to notice this witness thing here. So there's a witness, which is a mapping from truth variables to literals. This is substitution. We call it the witness here of this rule. And the thing is, you can look at this witness in 2 different ways. On the one hand, you can look at it as a syntactic manipulation of a formula. So just replace each variable by whatever the witness tells you to replace it by. Yeah. And on the other hand, you can view it as a manipulation of assignments, namely, well, just by this mapping an assignment, patching it up basically to first applying the witness and then the assignment. So you can look at it in 2 different ways, and these ways are compatible in the sense that an assignment satisfies the patched up formula, even only if the patched up assignment satisfies the original formula. Now, what does this redundance-based strengthening characterization now tell us? Well, it tells us a constraint is redundant even only if F and the negation of the constraint implies F and the constraint patched up with this witness. And how should you read this? Well, the thing that's going on is if you have any assignment that satisfies F, but that you have lost by adding the constraint C. So it satisfies F, but it falsifies C. What this then tells you is, well, you can patch up this assignment with this witness to get a new assignment that does satisfy F and that does satisfy C. Yeah. So if you would have this, then you're sure that even though you might lose some solutions, you will not lose all of them, because for every solution you lose, the witness tells you, patch it up like this, and here's a solution for you that satisfies both F and C. Now, this in itself, whether there exists such a witness, cannot be checked easily. So what you should do if you want to use this rule in practice is you should, on the one hand, specify the witness, and secondly, you should also make sure that all the constraints that you have to prove on the right here are easily provable. For instance, they could be rep constraint, and for instance, Ciaran also talked about syntactic implication. They should follow super obviously from F and not C. These are the conditions to satisfy. And how can we do this? For instance, to derive these pseudo-Boolean constraints encoding this fresh variable? Well, let's try it. We could say, first we want to add, say, the second constraint in this case. So we need to check that F and the negation of this second constraint implies that F and the second constraint are satisfied after patching up with some witness. And what we're going to do now is we're just going to take a witness that maps A to 0, and implicitly all the other variables are just mapped to themselves. So our witness maps A to 0. What does that do? Well, this constraint is unsatisfied because A is just false, and then this is trivially satisfied. And we're not even touching any of the variables that occur in F. So if F was satisfied here, then it clearly entails itself. So this is the easy step. The next constraint is a bit more difficult because now we don't just have to show that. So now we already have derived one constraint. And so we're going to try to do the same thing as before. We're going to try to take our witness to just give A the right value. But the problem is that we have a proof obligation now that we're not messing up the constraint that we added before. Yeah. So how are we going to do this? Well, so we claim that this witness still works. Just setting A to 1 still works. F is still untouched, so basically F implies itself, so this is going to be very easy to check. This constraint is satisfied just because we're setting A to 1, yeah. But we need to show that also this one is implied after patching up. And the reason this works is, well, if the green constraint here is violated, then it must be the case that X is true and Y is true. Otherwise, this one can never be violated. But if X is true and Y is true, then this constraint can never cause any problems because X is already giving us 1, Y is giving us 1. Well, that's 2 together. So this works. Now, there's 2 applications of this in the slides. One is running CDCL solvers on pseudo-Boolean inputs, which requires translating pseudo-Boolean formulas to clauses. And if you want to do that, you're going to need extension variables, and you're going to use this rule. And the second one is doing parity reasoning or XOR reasoning. You can also do this very neatly by introducing some new variables with this redundance rule, but the details I'm going to skip now. What I'm going to do instead is I'm going to go to an optimization setting, and I'm going to see, well, what happens to this redundance rule if we're doing optimization. So if we're doing pseudo-Boolean optimization, we don't just have this formula, but we also have some objective. And I'm using capital F here to denote the formula and small f to denote the objective, and the linear term that we're optimizing, minimizing. And of course, one thing that we should take care of is that, well, we're using this witness to patch up solutions. So we're saying, well, we're willing to lose some solutions, but if you lose some, this is a way to patch them up to get a new solution. Of course, if this way to patch them up would give us worse solutions in an optimization setting, we wouldn't be very happy with that. So we're just adding one extra proof obligation here on the right, saying that, well, you should be able to prove that whenever F is satisfied with C falsified, so whenever we're losing a solution, the patching up that we're doing gives us a smaller is better, a better objective value. And this works well. So this works well for optimization, but we can do even better. And in which case can we do better? Well, we can be a little bit more aggressive if our witness does not just guarantee that our newly produced solution is at least as good, but if it's strictly improving our solution. And that second rule we will call the dominance rule. Namely, it will allow us to add a constraint C if this condition is satisfied. And what's important to note here is, on the one hand, we're getting a strict inequality here now. So we're saying, well, we're getting a stronger proof obligation that our objective needs to be strictly smaller. But on the other hand, we're not forced to prove anything about C on the right-hand side anymore. So what we're saying is, whenever you have a solution F that falsifies C, you can patch it up to get a solution of F that's strictly better. And that might or might not falsify C. We don't know about that. So this will turn out to be very useful for doing symmetry breaking. Of course, you might wonder, why is this sound precisely? Well, suppose you have some solution. It satisfies F, but falsifies C. Patching up gives us a solution that still satisfies F, but that's strictly better. Now, there's two possibilities. Either it already satisfies C, and then we're done. Then we're sure that we didn't lose all our optimal, that alpha was not an optimal solution when we discarded it. Or it doesn't satisfy C, but then we can patch it up again. Then by patching it up a second time, we again get something that satisfies C, and that's strictly better. And we can keep on doing this. If it satisfies C, we're done. If it doesn't satisfy C, we patch it up one more time. And since we're in a finite domain setting, we only have a finite number of assignments, this decreasing chain cannot go on ad infinitum. So at some point it must stop, and at some point we must have found some solution that we preserve. So we're not making it explicit how exactly to get to that solution, but we know that by doing this possibly multiple times, this patching up, we will eventually get to a solution that we preserve. So this is still sound to do this. All right. We can even make it a bit stronger. The details are in the paper. But in fact, I gave you an argument why we don't have to prove anything about the constraint we're adding now. Actually, this dominance rule, you don't need to prove anything about any of the constraints you've derived before. So if you have previously derived lots of other constraints, all you need to do is show that your original formula is satisfied after patching up and that your objective is strictly decreasing. So I'm not going to give you the argument of why it's correct now, unless there would be any questions about it. But you see, we're making one proof obligation stronger here with the Fs that we're strictly decreasing, but we're losing a lot of other proof obligations. And for symmetry breaking, we're gonna use this a lot. And what you can also do is you can switch the order during the proof, switch between different orders in the same proof. But I will not show you anything that really does that, except for one trick I'm going to do. When I'm doing symmetry breaking for set, I'm going to pretend to be solving an optimization problem. First, a couple of small examples of what we can do with symmetries. In constraint programming, you might, this puzzle is well known, the crystal maze puzzle, where the goal is to put a bunch of numbers. You have to put a number in each of the circles here, and numbers between 1 and 8, and adjacent circles cannot have consecutive numbers. And when people solve this with a constraint solver, what they will often do is they will do some manual symmetry breaking. They might add symmetry breaking constraint because they see, well, there's we can mirror vertically, so we can always, without loss of generality, we can assume that there's a smaller number in A than in G. They might also see that, well, there's a horizontal mirror symmetry, so without loss of generality, we can assume that A is smaller than B. And they might also see, well, there's also a value symmetry, so without loss of generality, we can assume that A has a value that's at most 4. Just by swapping 1 and 8, 2 and 7, and so on. Now, what you can wonder is, well, hold on a second, you're breaking lots of different symmetries. Can I do all of these at the same time? And if you stare long enough at it, you'll see that the answer is yes. And in a certain sense, the answer is yes, because all of these constraints are trying to make A small. Now, instead of relying on the human to check that whatever he's doing with the symmetry breaking is indeed valid, you could introduce these constraints inside of the proof. Namely, we're not going to assume these symmetry breaking constraints in the input, but we're going to introduce them inside of the proof. And using the dominance rule, you can do this without knowing any group theory. Yeah, so the VeriPB doesn't know any group theory. So we can prove that it's okay to add these constraints without loss of generality. So this dominance rule allows us to reason without loss of generality here. And well, what's still currently not available is a complete toolchain that really supports doing this, doing the manual adding and getting the order out of the constraints that you want to add, and then writing out the proof automatically for you. So we did this manually on some examples, but there's no automatic toolchain yet. A second example where you might encounter symmetries, or even in this case, not just symmetries, but even a dominance relation, is in maximum clique. So for instance, if remember this maximum clique problem, where you're searching for a large clique inside a graph, and there might be two vertices here, vertex 2 and 2b. And what a max clique solver might decide is, well, I can just ignore vertex 2b because all of its neighbors are also neighbors of vertex 2. And 2 and 2b are not connected. So if I find any solution with 2b in it, I might, well, just throw 2b out and take 2 instead, and this will be at least as good. You can also certify this using dominance, and you can even do it when the constraints, when these dominance relations are detected during search. So you don't have to detect them in advance. You can do this lazily during search. Whenever you find such a relation, you can add a proof line certifying this, and VeriPB will be happy with it. And then I'll give you a little bit more examples of how we did symmetry breaking for set solving. So our strategy for doing this consists of 3 steps. First, we're going to pretend to solve an optimization problem. So set is a decision problem. We're just looking, does there exist an assignment? Instead of solving this decision problem, we're going to pretend to solve an optimization problem, namely search the lexicographically smallest satisfying assignment. Yeah. What we're going to prove is that this optimization problem is unsatisfiable. So obviously, the original decision problem was also unsatisfiable. The second step will be, well, if we find a symmetry, we're going to derive a lex leader constraint, and this will be a pseudo-Boolean constraint saying, I'm interested in assignments that are lexicographically smaller than their symmetric counterpart. So this is what this constraint is saying. Namely my objective, which is in our case, a large term expressing lexicographic leadership. Our objective is smaller than or equal to the objective after applying the symmetry. So the objective value of the symmetric assignment. And you can write this down, what it means in terms of literals. Of course, SAT solvers, they don't understand pseudo-Boolean constraints. So the third step, and I'm not going to give you the details of how we do this, but the third step would be then that you translate the pseudo-Boolean constraint into a bunch of clauses that the SAT solver actually understands. Yeah, and we implemented all this. We ran some experiments with it. The results are somewhere in the backup slides. And basically, the gist is you can do this without any noticeable overhead to the symmetry breakers. And this is a completely automated tool chain that detects the symmetries, breaks them, well, first then in a pseudo-Boolean form, and then translating it into clauses so that the SAT solver understands what we're doing. I see numbers popping up on the chat. Are there any questions I should answer right now? Because I don't see the questions appearing.
I think there are some just no questions in the chat.
No question. Okay, so then let me continue. So just to give a small example of the symmetry breaking, we here have a pigeonhole principle formula. We have variables Pij, and their meaning is Pij is true if pigeon I goes in hole j. And I'm going to focus here on pigeon symmetry. We can also do this for symmetries of holes or combined symmetries. But if I write sigma 1, 2, it means swap pigeons 1 and 2. Yeah? And in our case, well, this is also, if I write sigma 1, 2, 3, 4, it's a symmetry that shifts all the pigeons. So it puts pigeon 1 in the hole of pigeon 2 in the hole of pigeon 3, and so on. And the order that we have here is, in words, it says, I prefer to put pigeon 1 in the smallest possible hole and next pigeon 2, and so on. And you can write this as a pseudo-Boolean objective, where first all the variables related to pigeon 1 are appearing. Now, suppose we want to break a single and a simple symmetry. For instance, the symmetry that swaps pigeon 1 and 2. And what I would like to do is I would like to add this symmetry breaking constraint C12, saying that I only want assignments that are at least as good as their symmetric counterpart under swapping pigeons 1 and 2. So at least as good means pigeon 1 in a small hole and so on. And then pigeon 2 in a smallest possible hole and so on. So this is in pseudo-Boolean notation. This would be the constraint we want to derive. Namely, my objective should be at most the symmetric counterpart of it. So pigeon in words, this would say pigeon 1 goes in a smaller hole than pigeon 2. Yeah. And we don't even need dominance here. We can actually just do this using the redundance rule, because the redundance rule, remember the optimization version of it, what it said, well, if you have F and if you have the negation of the constraint, that should imply F after applying the symmetry, but that's just F again. And the constraint after applying the symmetry, and our objective should not get worse, should be at least as good. Yeah. If you fill in all the details, if you fill in this C12 becomes this inequality here, and then you push the negation through, and then here on the right, you apply the symmetry to F and to F after applying it, what you'll see is, well, applying this symmetry twice does nothing. Swapping pigeon 1 and 2 and then swapping it again does nothing. So on the right, we're going to get an F. On the left, we're going to get F under sigma 1, 2. If we fill this in, what we actually see is that on the left, we have something that clearly implies these two inequalities on the right. Yeah, because this is just saying F is strictly greater than its symmetric counterpart. And this is saying that F is at least as great as its symmetric counterpart, and this one too. Yeah. So why have I been talking about dominance? Well, this idea of doing symmetry breaking in this way, well, on the one hand, this I should still mention, this is very similar to DRED symmetry breaking, if you're familiar with this work. But so there are two problems with the way we're doing it now. Namely, it doesn't generalize if you want to break more than one symmetry, and they touch, say, the same pigeons or the same holes, they touch the same variables. And it also doesn't work if you're breaking complex symmetries. So why does it not work intuitively when you're breaking two symmetries? Well, roughly, your witness for fixing up the second one might potentially falsify the things you've derived before. Yeah. And why does it? So we might have to, if we really want to get to a solution, we might first have to use the one patch and then use the other patch again, and then alternate between them till we have a good solution. And for complex symmetries, it also doesn't work because we might have to apply, well, just shifting all the pigeons one hole, for instance, might not result in something that's lexicographically smaller than its counterpart yet. We might have to do this 2 times. We might have to do this 3 times. And we don't know in advance how many times we'll have to do this. So you could try to fix this, or we could try, well, let's take the dominance rule. Let's try to break this with the dominance rule. And so remember, this is the constraint you want to derive. And we claim here, you can do this with just using the dominance rule and just using the permutation, so using the symmetry as the witness. And this is what we would have to prove for the dominance rule, that our formula and the negation of the constraint implies our formula after applying the symmetry, but this is just syntactically equal to the original formula, and that we're getting a strict improvement in our objective. But remember from last time, remember from last time that this negation of this constraint is actually just giving you, this is actually just equal to that. So there's nothing left to prove. Yeah, this is just syntactically everything on the left is the same as everything on the right. So this is surprisingly simple. Yeah, doing this with the dominance rule is surprisingly simple. It generalizes. You can do this for complex symmetries. You can do this for multiple symmetries. And why can you do it for multiple symmetries? Precisely because you don't care about things you've derived before. In a certain sense, this order is coordinating between the different things that you're adding, because between the different breaking constraints that you're adding, and it's making sure that everything stays consistent. All of them force all of the witnesses go down in the same order. So in that way, we know that all the symmetry breaking that's happening is consistent. So crucial here is your witness doesn't need to force that all derived constraints are satisfied. Its main job is to just produce better assignments. Yeah. So our message to you is, well, if you have an interesting solver, make it output proofs. Make it, and you can make it output proofs in the VeriPB proof format, for instance. You can find it here. It's documented. There are worked out examples in several of our papers, and even more in the PhD thesis of Stefan Gocht. And we're always happy to collaborate. So if you have interesting proof logging problems, talk to us. If you're a student looking for a nice position, also talk to us because we're hiring. And there's lots of challenges in the road ahead. For instance, related to verification, getting not just, for instance, for the graph problems, it would be very interesting to have formally verified encodings. Now we still have to rely on the encoding being simple enough to obviously represent the problem at hand. But if even the encoding could be formally verified, that would be better. And formally verified proof checkers, there has been a question about this already. There's work on this, so expect to see something in the near future, I would guess. Related to verification, there's also performance of the proof verifier, which we still need to improve, I think. Related to proofs, one interesting open question is whether we could do something similar to substitution proofs, where you're able to reuse parts of your proof in later on. But there's also lots of things to prove, for instance, such as approximate counting, that you can prove bounds on your counts, sampling, doing other types of optimalities such as Pareto fronts, making our proofs that we produce smaller, minimizing them in some way or trimming them. In the DRED, there has been the famous DRED trim tool, which does this for you by going backwards through your proof. So this would also be something to look into in the future, whether we can get something similar for Pseudoboolean proof logging. And of course, there's many solving algorithms for which there is no proof logging yet. So on our agenda up next is to just do this for all of them. And of course, we cannot do this alone. So if you're interested in this, come talk to us. And that's it for this presentation. So that's the end, or should we say the beginning of a new era of trustworthy combinatorial search. So if there are any questions, I would be happy to answer them, or any questions for the previous speakers.
Hi. So I have a few questions, and I don't know who's most who knows most about this to answer. But if we consider a system like OR tools, so typically when you run OR tools in its most useful setting, it's multi-threaded, and it will run local search. And I'm guessing that's easy to handle because it just produces new satisfying assignments. But then there are other things like if you run it, it has a MIP solver, and it will have lower bounds, and it will add cuts based on that, which sort of like appear from magic, from nowhere. I'm guessing that might be hard to log a proof for, because it includes a whole simplex of the whole problem.
So maybe one thing that would be relevant to mention here is that also in the MIP community, there is some progress on proof logging, on producing proofs, and for, well, their advanced algorithms. So Ambros Gleixner has been working on this.
Okay.
We can get your reference if you're interested in that. So it's not impossible to do this. Of course, there's lots of things related to floating point arithmetic and so on that has to be taken care of there as well. So there's lots of challenges, but it's not something completely impossible to get.
Yeah. I think OR tools is using a fixed point MIP solver just to get rid of floating point errors, and they try to solve it on a safe side so that they're always worse or for finding a lower bound.
Okay. So I guess the answer is, in principle, all the information is at some point available to get this proof, but it's a matter of getting it all out and to do this in a format that understands this. So.
And similar, this discussion about work stealing. Ciaran, you mentioned something about linearizing. So I'm guessing that so work stealing typically as far as all systems I know, you still work from like right after a decision has been made. So essentially, if you gave everything a unique identifier and said, okay, all my children are named this, and if you still work, you say I'm starting from this identifier. So I'm guessing that's something you would output in the log, and then you just have to reorder it.
So the thing I don't quite like about this is somehow that fixing everything up is linear in the length of a proof. What I think you can do is, so whenever you have stolen work, you introduce an extension variable for that piece of stolen work. Okay. And then you sort of keep track of this, and what you end up producing is when a worker finishes its active chunk of work, it's produced a proof saying, okay, here are all the things I've done. And if the following extension variables, which represent stuff that people have stolen from me, are also false, then I have proved that this subtree contains no solution. And then as other people finish pieces of stolen work, they will actually output, aha, now I have shown that this extension variable is in fact set to false. And all of this stuff disappears. And I think this works. There is a slight issue with deletions and memory usage. That what I haven't worked out is whether you can do this in such a way that you can delete bits of a proof aggressively that you're not going to use anymore.
Yeah.
But I think extension variables give us a way of doing basically what you're suggesting, but without having to explicitly make any of the proof system aware of work stealing or multi-threader or anything else like that.
Okay.
I think this works.
Yeah, I was thinking more like you could essentially textually reorganize the blocks of proof by outputting these identifiers and saying that, okay, at this point I have these children and I am the child X.
Yeah, although then, because somehow you have to check that the proof is actually still a DAG when it finishes, so somehow you haven't introduced circular reasoning into this. Yeah,
of course, but so, I mean,
yeah,
any work stealing system is essentially exploring a tree that you can just reorder any way you want. So it's just that you output the bits of information in the wrong order.
Yeah, and then somehow something somewhere has to verify that this is actually a tree. Is the tricky bit.
Yeah, I mean you have your ID and you have your children's ID, so it's some, again, it's doable. I'm not saying it's easy or efficient. And one other thing I was thinking about is if you look at things like CP optimizer, and they have their implication graph, which is 2 XOR or a 2-sat system, which has also some interesting propagation properties that I think might be. It should be proof loggable easily enough, but it's again one of these global things that might give large steps in the propagation.
So we know how to do Gaussian reasoning.
Yeah.
Do we? I think we even have slides on that somewhere, possibly. So I think that's doable.
Yeah.
But again, it's finding somebody who can understand exactly what's actually going on and sitting down and doing all the proof logging for it.
Yeah.
So.
Yeah. That's interesting. Thanks.
Any further questions?
So then I think we should thank everybody for sticking around till the end. We apologize for going slightly over time compared to what we first planned. but thank you for listening, and hope to see you again.